Your phone just unlocked when you looked at it. You didn't type a PIN. You didn't press anything. It just looked at your face and opened. Now think about that for a second. How does it know it's you? How does it know it's not your sibling or a photo of you or just some random face in the room? Someone had to teach it. But here's what's strange. No one sat down and wrote out a description of your face. Nobody coded in her nose is this shape or his eyes are this far apart. There are no rules like that anywhere in the software. So what's actually going on? That question is exactly where machine learning begins. Let's try the obvious approach first. Say you want to build a program that can tell a cat from a dog. Simple enough, right? You're a programmer. You sit down and you start writing rules. If it has pointy ears, it's a cat. Okay, but some dogs have pointy ears. German Shepherds, for example. If it's small and fluffy, cat. Chihuahuas are small and fluffy. If it has whiskers, cat. Some dogs have whiskers. You keep going and the rules keep breaking. For every rule you add, reality hands you an exception. And the more rules you add, the more they start contradicting each other. This isn't a skill problem. You could be the best programmer in the world and you'd still hit the same wall. Because the real world is messy. Categories bleed into each other. There are 1,000 ways for a thing to be a cat, and none of them are clean enough to reduce to a neat list of if statements. Language is the same. Spam detection, fraud detection, medical diagnosis. Anytime you're trying to label something complex, the rules approach collapses. There has to be another way. Here's the shift. What if instead of writing the rules yourself, you let the machine find them? You don't tell it what a cat looks like. You show it 10,000 pictures of cats and 10,000 pictures of dogs. And you tell it, these are cats, these are dogs. Figure out the rest. But it changes everything. The machine isn't memorizing the pictures, it's looking for patterns. Patterns in the shapes, in the textures, in the proportions. Things that tend to appear in cat images that don't tend to appear in dog images. It builds up a kind of internal sense, not of rules, but of tendencies. And the beautiful part, you never have to explain it. You don't have to understand what patterns the machine found. You just give it data and it does the work. Now, this idea has a name. We call it learning from examples. And it's the foundation underneath almost all of modern machine learning. The program that unlocks your phone with your face, it was shown millions of faces. It found patterns so subtle that no human could have written them down, but it learned them from data. Let's make this real with something classic. Handwritten digits, numbers 0 through 9, written by hand by thousands of different people. Some people write their 7s with a little crossbar. Some people's ones look like lowercase l's. Everyone's handwriting is slightly different. There's no single correct way a digit looks. So how do you build something that reads them anyway? You collect a giant data set, tens of thousands of handwritten digit images, each one labeled with the correct number. This collection is called the training set. It's the examples the machine learns from. You feed all of it into a machine learning algorithm. The algorithm goes through every image, every label, and it starts finding what pixel patterns tend to go with which numbers. Where do the curves cluster? Where do the straight lines show up? It adjusts and refines over and over until it gets good at matching patterns to labels. This whole process is called training. After training, you give the model something it's never seen before, a brand new handwritten 7, one that wasn't in the training set. And the model looks at the pixel patterns in that image, compares them to everything it learned, and makes a prediction. I think this is a 7. That's it. That's the core loop. You train on labeled examples, you predict on new ones. The model doesn't know what a 7 is in any meaningful sense. It doesn't understand numbers. It has no idea what counting is. But it's very, very good at recognizing the visual pattern that humans consistently label as 7, which honestly is all you need it to do. That same loop, show data, find patterns, make predictions, is running underneath almost every piece of software that feels intelligent today. The reason it got powerful enough to do all of that isn't magic. It's because we gave up on writing rules and started giving machines data instead. More data, better algorithms, more computation. That's been the story of the last decade. And it's still going. So let's pull this together. Hand-coded rules break when the real world is messy. And the real world is always messy. The machine learning answer is to skip the rules entirely. Instead, collect labeled examples. Train a model to find the patterns in that data, and use those patterns to make predictions on new inputs. It sounds almost too easy, and in some ways it is. The hard questions come next. Which algorithm do you use? How does it actually find those patterns? What happens when it gets things wrong? Those are exactly the questions the rest of the series is going to answer. Next episode, we're starting with one of the oldest and most surprisingly clever ML algorithms out there. No neural networks, no complex math. Just a simple idea. If you want to know what something is, look at what's around it. It's called k-nearest neighbors. And once you see why it works, you'll start noticing it everywhere.